The sheer intensity of solar flares has been drastically underestimated. These astounding bursts of energy from the sun might burn at temperatures far beyond what scientists once thought possible. But here's where it gets controversial. New findings suggest solar flares can reach a staggering 180 million degrees Fahrenheit. This is more than 6 times hotter than previous estimates by solar physicists, shaking up long-held assumptions about the sun's powerful outbursts. This eye-opening revelation comes from advanced observations by NASA's Solar Dynamics Observatory, which continuously monitors solar activity. On January 12, 2015, it captured an image of a mid-level solar flare that became a key piece of this puzzle. Alexander Russell, a physicist at the University of St. Andrews in Scotland, described the astonishing temperatures they calculated as a crazy number, something he and his research team initially found hard to believe. To understand why this matters, it's important to grasp how solar flares form. They happen when magnetic energy stored in the sun's atmosphere suddenly releases and accelerates particles like ions and electrons to extreme speeds, heating them intensely. Until now, scientists mainly measured the temperatures of electrons during these flares using telescopes and assumed that the ions, heavier charged particles, would share the same temperature. But that assumption may be fundamentally flawed. Recent computer simulations and measurements taken in space near Earth have hinted that ions heat up far more than electrons do during a flare. Exploring this further, Russell and his colleagues performed detailed calculations and discovered that the actual temperature of the ions in solar flares could soar above 100 million degrees Fahrenheit, potentially even much higher. James Drake, a physicist at the University of Maryland who was not involved in this study, has spent years investigating how magnetic fields accelerate and heat these particles. He emphasizes that the significant difference in temperatures between ions and electrons has been largely overlooked in previous solar flare research. "We've been confronting the solar physicists," Drake explains, telling them that even though they've measured electron behavior in detail, they're missing a critical piece. This is a bold statement that invites debate about past methodologies and interpretations in solar physics. Drake welcomed the new findings, seeing them as a vital step toward a clearer, more accurate understanding of solar flares. This progress isn't just academic. Gaining deeper insight into flare dynamics could improve how we shield satellites and protect astronauts from the potentially damaging effects of these intense solar storms. Looking ahead, Russell reveals that his team is already developing more sophisticated models that simulate solar flare development by incorporating the stronger ion heating. These efforts may transform our grasp of solar phenomena and prompt a reevaluation of how space weather impacts our technology and safety. So what do you think? Does this breakthrough challenge how we've traditionally studied solar flares? Could redefining temperature dynamics in flares change how we prepare for space weather events? Share your thoughts, because this new understanding might very well ignite lively discussions among scientists and space enthusiasts alike.